Good morning, good afternoon, or good evening, wherever you are in the world, and welcome back to the channel. Today, we are going back to study and embarking on a journey not just through space but through revolutionary concept that promise to change how we travel across the cosmos. We are talking about the foldable solar sails, but not just for the propulsion. We are going to explore their incredible potential as a future of aerobraking and the atmospheric re-entry. For decades, some explorations have been testament to human ingenuity. We have launched probes to distant planets, established a permanent presence in orbit, and even dreamed of venturing to other star systems. But beneath the glamour of the rocket launches and the cosmic discoveries lies a persistent fundamental challenge. How do we slow down? Landing a spacecraft safely on a planet with an atmosphere or even returning to Earth is one of the most complex and dangerous maneuvers in spaceflight. It is a delicate dance between speed, friction, and heat, often relying on massive heat shield and precious limited fuel. What if there was a better way? A way to use a very thin wisp of another planet's atmosphere to gently, efficiently, and precisely bring spacecraft to halt. Enter the foldable solar sails. While often envisioned as cosmic wind catchers propelling us across the void with sunlight, their potential extend far beyond acceleration. Today, we will uncover how these ingenious structures are being engineered to become the ultimate air brakes of tomorrow's spacecraft. So, buckle up because the future of space travel is about to get a whole lot smoother. To understand the innovation of the solar sail in aerobraking, we first need to understand the problem they're trying to solve. Let's talk about the traditional aerobraking. It's a technique where spacecraft use the drag from planet atmosphere to slow down, reducing the amount of propellant needed for orbit insertion or descent. Think of it like a swimmer putting their hands flat against the water to slow down. Missions like NASA's Mars Global Surveyor and Mars Reconnaissance Orbiter successfully used aerobraking. Instead of firing powerful engines to enter a low orbit around Mars, they made hundreds of shallow passes through Martian upper atmosphere over several months. Each pass, tiny bit of fraction, slowed them down, gradually lowering their orbit. While effective, traditional aerobraking comes with significant challenges. Firstly, the precision is paramount. Too deep into the atmosphere and the spacecraft will burn up. Too shallow, it takes too long or doesn't slow down enough. Secondly, the heat. The friction generates immense heat, requiring robust thermal protection system. And thirdly, the time. The process can take weeks or even months, extending missions timelines and increasing operational costs. Finally, the mass. The heavy heat shields and propellant tanks add significant mass to the spacecraft, which means more expensive launches. Every kilogram launched into space costs thousands, sometimes tens of thousands of dollars. This is where the concept of using foldable solar sails for aerobraking begin to shine. Imagine a system that could achieve the same braking effect, but with far greater control, less thermal stress, and significantly reduced reliance on heavy consumable resources. That's the promise of this solar sail. Let's clarify what solar sails are. Most people know them as propulsion systems. They work by harnessing the slight but continuous pressure exerted by the photons from the sun. Think of it like a sailboat catching the wind, but instead of wind, it is sunlight. Over long distances, this tiny push can accelerate a spacecraft to incredible speeds without a single drop of fuel. Mission like Japan, Icarus in 2010 and the Planetary Society's Light Sail 2 have successfully demonstrated solar sailing for propulsion. These spacecraft unfurl vast, ultra thin membranes, often thinner than human hair, across enormous areas. But it is the very characteristic, their enormous surface area and incredibly low mass, that makes them so attractive for aerobraking. The key principle here is the drag. When a solar sail unfurled to perhaps hundreds or even thousands of square meters enters the wispy upper atmosphere of a planet, it acts like a giant parachute. The vast surface area catches huge amount of atmospheric molecules, creating significant drag even where the atmosphere is incredibly thin. Because the sail itself is so light, this drag effect is exceptionally efficient. This is the fundamental shift. Instead of a compact spacecraft relying on a relatively small, heavy heat shield to generate drag and dissipate heat, we have a vast lightweight sail designed to maximize drag while distributing any thermal load over a much larger area. This significantly changes the dynamics of atmospheric interactions, and for the foldable aspect is crucial. This isn't just a giant sheet. There are precision engineered structure that can be compactly stored during the launch and cruise, then reliably unfurled to their immense size when needed. This deployment and retraction capability is what makes them versatile and reusable for different mission phases. So, how exactly would this work in practice? Imagine a spacecraft arriving at Mars. So, instead of firing its engine extensively to slow down into orbit, it deploys its massive solar sail. As it makes its initial shallow pass into the Martian upper atmosphere, the sheer surface area of the sail dramatically increases the drag. This enhanced drag allows for a much more rapid and efficient slowdown compared to compact and efficient slowdown compared to the spacecraft actual engines. Critically, because the drag is spread across such a vast surface, and the heat flux, the amount of heat energy per unit area is significantly lower than what a traditional heat shield experience. This means less extreme temperature, less stress on the spacecraft systems. This reduced thermal load and had a profound implications. It could mean we need less robust, lighter, and therefore cheaper thermal protection system. It could also allow for a more delicate scientific instruments to be exposed to atmospheric environment without the risk of overheating. Furthermore, the ability to precisely control the sail's orientation and deployment open up new avenue for atmospheric control. By adjusting the angle of attack or even partially retracting and extending section of the sail, the mission control could fine-tune the amount of drag, allowing for incredibly precise aero capture maneuvers or even controlled gentle descent towards the planet's surface. This is a level of control far beyond the traditional heat shield offers. Think about it. What are the advantages? First, reduced fuel. Less need for larger propellant tanks for orbit insertion or deorbit burns. Reduced mass, lighter thermal protection system, and less fuel directly translate into less mass, making launches cheaper, allowing for more scientific payloads. Increased safety. More controlled deceleration reduce the risk of overheating or uncontrolled trajectories. Faster operations. Potentially fewer orbital passes to achieve target orbit, shortening the mission by using aerobraking phase. Versatility. The same sail used for propulsion during cruise could then be repurposed for aerobraking. This dual purpose functionality is the key here. A single system serving two critical functions during a mission lifecycle represents a massive leap in spacecraft design and its efficiency. It truly makes these sails a cornerstone of the future deep space exploration. Of course, Like any cutting edge technology, there are significant challenges to overcome. Things like material science, because the sails need to be incredibly thin, lightweight, and yet remarkably strong to withstand the forces of deployment, the harsh space environment, and the stresses of the atmospheric interaction. Materials like Captain, Mylar, or advanced composites are constantly being refined. They must resist the degradation from solar radiation, micrometeorite impacts, and the temperature extremes. Next is the deployment mechanism. Unfurling a sail the size of a football field or even larger in vacuum of space with pinpoint accuracy and without snag is an engineering marvel. This requires sophisticated booms, motors, and control systems, all designed to operate flawlessly in an unforgiving environment. Then, atmospheric interaction modeling. Understanding precisely how these vast flexible structure will behave in extremely thin atmosphere where the traditional aerodynamics don't fully apply is quite complex. Scientists need to model potential flutter, oscillations, and how precise the adjustment can control the drag without introducing any instability. Despite these challenges, progress is rapid. Agencies like NASA, ESA, and private companies are heavily investing in this research. One exciting concept being explored is the Solar Cruise mission, designed to demonstrate high power solar sailing. While primarily for propulsion, the data gathered from such mission will be invaluable for understanding the behavior of the large sails. Another area of the focus is low-cost CubeSat mission that are testing novel deployment systems and advanced sails material in Earth orbit, paving the way for larger, more complex applications. The ultimate vision of this technology includes not just robotic probes, but eventually manned mission. Imagine a human habitat module gently guiding into Mars orbit by its solar sails, minimizing the need for precious fuel reserves that could instead use for surface operations. The promise of the foldable solar sail for aerobraking and re-entry is about more than just efficiency. It's about enabling a new era of space exploration, making it more affordable, safer, and ultimately allowing us to go further and explore more deeply than ever before. So, as we look into the vastness of the space, the challenges of getting there and getting there safely are immense. For too long, our methods of slowing down have been characterized by brute force, massive heat shields to endure extreme temperatures, or large quantities of fuel to counteract orbital velocities. But the future is pointing towards elegance and efficiency. Foldable solar sails, initially conceived as a means of propulsion, are now emerging as a powerful solution for one of the space travel's most critical hurdles, aerobraking and atmospheric re-entry. Their ability to provide massive drag with minimum mass distribution, thermal loads effectively, and offer unprecedented control during atmospheric passes transform them into a dual-purpose marvels of engineering. They save fuel, reduce launch mass, enhance safety, and accelerate mission timelines. This isn't just a theoretical concept, it's a technology actively being developed and tested, promising to open up a new frontier from delivering scientific payloads to distant moons with thin atmospheres to gently guiding future human explorers to surface of Mars. Foldable solar sails represents a fundamental shift in how we interact with cosmic environment. The era of foldable sails is unfolding before our eyes, promising a future where our journey through cosmos is not just about reaching our destination, but about arriving with precision, efficiency, and a newfound grace. So, friends, thank you for joining me on this exploration of foldable solar sails. What are your thoughts on this revolutionary technology? Let me know in the comments section below. Don't forget to like this video, subscribe for more insights into the future of space exploration. Until next time, keep looking up.